Okay, welcome to the last part of lecture 5. In this part, I will be looking at a combinatorial puzzle, and that is mostly because we will prove a polynomial bound for the maximum number of dichotomies given that there is a breakpoint. And that we'll do in the next lecture, but we will start developing certain concepts and certain definitions right in this lecture. So the very first definition that we're looking at is, what does this mean when I'll say that shatter a data set? What does that mean? What does like to shatter mean? Let's say I have like x1, x2, and so on up to xn points, right? And let's say there is a hypothesis set H, right? And obviously the maximum number of dichotomies we know, like for a binomial problem, binary problem, sorry, that's not a binomial. So if the maximum number of dichotomies that can be implemented, the worst case is 2 to the n, we know that. Now, if my H can implement, all possible dichotomies, so like all possible dichotomies, which is obviously 2 to the n, right? Then I will say that H shatters this data set, this number of points, right? So this is what shatters mean, right? And we have seen when certain hypotheses can shatter all 2 to the n points, some shatter less than 2 to the n points, and how that happens, right? So essentially, if we can implement all those dichotomies, all possible dichotomies with H, then we say that H has shattered that like set of points, essentially. Okay, so having said that, let's move on to this combinatorial puzzle, which looks something like this. Okay, let us assume I have like x1, x2, x3, 3 set of points, and I'm trying to implement all possible dichotomies. Well, you can tell all possible are 2 to the n, and here I've just implemented 4 of them. And just to make things easier, all these like empty circles, they mean it's negative, and if it's a filled black circle, it means it's a positive value. Okay, so having said that, here we are just like looking at 4 cases, as I said, and what we are interested in finding is like those 4 dichotomies that cannot shatter any pair of 2 points. Okay, let me write it down. So we are interested in finding 4 dichotomies out of the 2 to the n, which in this case is 8. So 4 dichotomies out of these 8 that cannot shatter any pair of 2 points. Cannot shatter, notice, any pair of 2 points. What does that mean? Well, let me show you this. Here, obviously, okay, let me show you another picture that will make things clear. Here, yeah, this is a better way of understanding this. So the same 3 points, the 4 dichotomies that we just looked at, and if you only look at this part, which is x2 and x3, all possible values are there, right? Negative, 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 positive, positive, negative, and positive, positive. So these 2 points are shattered here. So what we wanted was to find out 4 possible dichotomies that will not shatter any pair of points. So of course, it's not shattering x1 and x2. As you can see, this and this is repeated, and this is repeated, right? So we have like a negative, negative, again, negative, negative, and then we have a negative, positive, again, a negative, positive. So x1, x2 wasn't shattered. So that pair wasn't shattered. But the pair x2, x3 was completely shattered because I have like all possible scenarios here. Right, so this is what it means when I say that 2 points are shattered. Okay, so moving on. Here is an example when no pair of points is shattered. We can look at it and try to understand what that means. Okay, let's focus on x1 and x2. Let's see if all points are shattered or is there a repeat. The moment you see a repeat, you know that there is like a possibility that this one of them could have been like a positive, positive. So this is definitely not shattered. Let's focus on x2 and x3 now. Here, this, okay, and this. So here is a repeat, right? So we have like a negative, negative, and a negative, negative repeat again. Let's look at x1 and x3. Okay, a negative, negative, positive. Okay, so here is the repeat, right? Negative, negative, and then negative, negative. So no pair of points is shattered, and I have those four dichotomies that I was looking for. So essentially, if you look at it, it's a combinatorial problem where we are trying to find out some number of dichotomies on some number of given points such that no subset of some size, which is 2 in this case, can be shattered by these dichotomies. And we are going to use that in certain things in the next lecture. But for this lecture, what I'm like the point that I like to make before we end this is that if n equals 4, not 3, so we found like the situation when n was 3, this was a situation when no pair of 2 points was shattered. Now, if I increased one more point here, instead of like 3 points, I have 4. How many possible dichotomies with no 2 points shattered? First of all, the number of dichotomies I'll have is 2 to the 4, which is 16. So out of the 16, how many can we come up with such that no 2 pairs are shattered, right? And this is left as an exercise for the students to work on. And of course, it's up to you. How do you want to come up with that? How do you want to count those scenarios wherein we have like all possible dichotomies, but with no 2 points shattered? You can list out all possible dichotomies and then just like pick those up, and or you can come up with some other way of like trying to find out the number of dichotomies that actually achieve this particular sort of result. And why are we interested in that is because we, as I said, we will be proving a polynomial bound using some combinatorial quantity that counts the maximum number of dichotomies given that there is a breakpoint, and we will be using that for a particular form of like a given hypothesis, and then we can apply it to any edge. So it's going to be really interesting in the next lecture. For this lecture, I leave you with listing out and just counting the number of how many possible. So the question is essentially asking you how many possible dichotomies are there with no 2 points shattered. Please go ahead and try that, and I will see you in the next lecture. Thank you.